I hope everybody is fine. Now let's continue from the previous video. Now in this video, what I'm going to do is to discuss alpha decay, but this approach is purely classical in nature, and as future lectures come, we will also subject this alpha decay to the quantum mechanical aspect. So here we want to just understand what is the classical approach of alpha decay. So, so what is alpha decay? It's basically this spontaneous, it is a spontaneous process of emission of alpha particles from radioactive nucleuses. And an alpha particle it is emitted by a heavy nucleus, and the nucleus is called as parent nucleus. And it has very large internal energy and is very unstable. And in order to release the extra energy, the parent nucleus emits alpha particle. So it emits alpha particle, and and the product nucleus, which is a different nucleus, basically is the daughter nucleus. And this daughter nucleus and alpha particle, they have recoil energies, right? And if we have to demonstrate this in a very sophisticated way, suppose this is my alpha particle X, A, and sorry, the nucleus, and it undergoes disintegration, and we will have alpha particle out of it, and we will have the daughter nucleus, and we will have alpha particle. Now, in order to conserve the linear momentum, the direction of this alpha particle, which is He4 and 2, will be in this direction, and the direction of this daughter nuclei will be in this direction. So this will be a new element, and what we'll have is here the mass number will go down by 4, and its atomic number will go down by 2. So let me assume that the velocity with which this daughter nuclei goes is Vd, and let me assume that Va V alpha is the velocity of the alpha particle, and what I have is a nucleus which disintegrates into the daughter nucleus and an alpha particle, and there this reaction can be written in a very simplistic way. It is X A Z. It undergoes radioactive disintegration, and we have Y A minus 4 and Z minus 2, and then we have He4 and 2. So this is our alpha decay. But in addition to this, since it's a spontaneous emission, it's a spontaneous decay. So here we will have Q value. So we'll have energy, and this Q can be calculated by simply taking the mass of X and subtracting mass of Y and mass of alpha particle, and multiply this by c square, and this will give us the Q value for this alpha particle, and and this Q value, you can also call it here as disintegration energy, and basically this energy is shared by this daughter nucleus and the alpha particle, and this energy which is shared between this daughter nucleus and alpha particle, it is in the form of kinetic energy. It has to be in the form of kinetic energy. Now we can have examples of alpha decay, like if we have uranium 238 and with atomic number 92, it can undergo alpha decay, and you can have thorium 234 and 90 atomic number with an alpha particle. That's He4 and 2. And we can have plutonium and 242 with atomic number 94. It can undergo alpha decay, and we can have uranium 238 with atomic number 92 and an alpha particle. And there are many other examples that can be used to show the alpha decay. Now let's try to understand this problem of alpha decay using the kinetic energy and the speed of these particles that I'm trying to talk about. Uh, so what is important here is we have to we have we have the mass of data nuclei. I would like to put it as MD here, and here the mass of alpha particle is M alpha, and here the mass of the parent nucleus is MP. Okay, now uh, let us apply the law of conservation of linear momentum. So, applying conservation of momentum. Okay, so what will that give me? That will give me md vd plus m alpha v alpha equals 0, because the parent nucleus was at rest, so its momentum before the decay is 0, and then we have the momenta of alpha particle and the momenta of the daughter nucleus. So that is mdvd plus m alpha v alpha, that should be equal to 0. That should be the case, and we would like to apply now conservation of kinetic energy. From here we can have this mdvd equals minus times m alpha and v alpha. So vd is minus m alpha by md times v alpha. And this negative sign is clear indication of for the conservation of linear momentum, and that's why the direction of the alpha particle is exactly opposite to the direction of this daughter nuclei that we have. So this is this is the velocity with which the daughter nuclei will move, and then applying conservation of kinetic energy, applying conservation of kinetic energy. So what will I write? 1/2 of m d vd square plus 1/2 of m alpha v alpha square must be equal to 0. No, it should not be equal to, it should be equal to q basically, yeah. Because the kinetic energy of the after the disintegration, the kinetic energy of daughter nuclei and the alpha particles is basically this what we call as disintegration energy, or Q value. Okay, that's the case. Now, what would I like to do here is that I would like to use this value of Vd in this equation. So, doing so, what would I have after this is, yeah, what will I have? I will have 1/2 of md times minus m alpha md times minus m alpha by md times v alpha v I have used for vd, so this is going to be square and this is also going to be square, and then what I will have is 1/2 of m alpha v alpha square is equal to q. That should be the equation, and we can move on. So what I'll have here is this minus will convert into plus. I will have 1/2 of m alpha square by md, because this md and md will cancel. Then I will have v alpha square plus 1/2 of m alpha v alpha square is equal to q. That should be the case, and I would like to have 1/2 out, and I would like to have M alpha out. I would like to have V alpha square out. What am I going to have inside is M alpha divided by MD plus 1 is equal to Q. And and what is this? This is the kinetic energy of alpha particle. So let me call it K alpha times M alpha by MD plus 1 is equal to Q. And now, what is M alpha? It is taking it in terms of atomic mass unit is it is 4 am dot u, and what is M daughter? It is a minus 4. That should be the case. So I can use this. What I'll get is K alpha times 4 by a minus 4 plus 1 is equal to Q. That should be the case. And from this, I can have kinetic energy of the alpha particle. So what will be that? That will be A minus 4 divided by A times Q. So this is the expression that I'll get for the kinetic energy of this alpha particle. That is that has come out of the parent nucleus. And and we can see that this kinetic energy is I would like to write it here. So let me have 3 here. Now this daughter nucleus that we have, it is very heavy as compared to the alpha particle. So most of the distinguishing energy that Q we have calculated here, that most of that Q appears as the kinetic energy of the alpha particle. So Q is mostly the kinetic energy of alpha particle. So should I say that this 1/2 of V alpha square is A minus 4 by A times Q. So I can write down this V alpha. That will be 2 by M alpha times A minus 4 by A. Yeah. So this will be the velocity with which the alpha particle will move. Now what we have both. We have the kinetic energy of this alpha particle and we have the velocity. Now alpha particle can escape from the nucleus if the potential barrier of the nucleus is of the order of the kinetic energy that we have calculated here. It should be of the order of this. and and that kinetic energy of alpha particle comes out to be nearly 5.4 mega electron volts on an average. And what has been found is that the height of the potential barrier of this nucleus, so this nucleus has a potential barrier, and that potential barrier is nearly 26 mega electron volts. And alpha particle, suppose alpha particle is here, and it has only 5.4 mega electron volts of energy. So if alpha particle that has come out of this nucleus has energy 5.4 mega electron volts, which is very less than that of 26 mega electron volts, classically it is impossible for this alpha particle to come out of the nucleus. So what we see here is that the classical physics cannot explain the theory of the emission of alpha particles from radioactive nucleuses, and this is because of the simple reason here: the height of the potential barrier is 26 mega electron volts, but the kinetic energy of this alpha particle is only 5 mega electron volts. So to cross this barrier potential, an alpha particle must have energy equal to 26 mega electron volt at least. But no alpha particle emitted by the radioactive nucleus possesses this much of energy. They have only this much of energy, and hence it should not escape the nucleus. It should remain there forever. And this problem of escaping of alpha particle from the nucleus, it was solved by Gamow mainly, and there were other people involved in this. Condon was there, and Gurney, and what they did, they gave the answer to this problem using quantum mechanics. And according to this theory, the motion of a particle in the neighborhood of this potential barrier is considered it's considered to be a wave, and it's found that there is small but finite probability that this alpha particle can tunnel, can leak through the potential barrier, even if its kinetic energy of the alpha particle is less than that of the height of the barrier potential that it has. So that kind of thing we'll be doing in the future lectures when we would like to understand the phenomenon of alpha decay. And here we clearly understand that we cannot explain alpha decay because classical physics, the Newtonian physics, has no answer for this, because the kinetic energy of the emitted alpha particle is very less than that of the potential barrier of the nucleus, which it has to cross in order to come out of the nucleus. Now let us talk about beta decay. And what is beta decay? It's basically it's a spontaneous process of emission of beta particles from a radioactive nucleus, and we call this kind of decay is called as beta decay. And uh, beta decay is of three types, and one is called beta minus decay, and another is called beta plus decay, and uh, the next one is called electron capture. Electron capture. And this beta minus decay is an electron, and beta plus, this is an electron simply, and this beta plus is positron, and positron is actually electron, but with opposite charge, and and you may also call it as an antiparticle of electron. So, talking about beta negative decay. In beta negative decay, what happens is the neutron inside the nucleus. We have a nucleus. The neutron inside the nucleus is converted into the proton, and an electron-like particle known as beta negative, is emitted from the radioactive nucleus. And if I have to write down this reaction, I have X, A, and Z. So what I get is Y, A, Z plus 1 plus beta negative and plus Q beta. Now, this is very surprising that nucleus, it does not contain, there's no electron inside the nucleus. And then how a nucleus can emit an electron? And this electron is this is an electron-like particle which is emitted by the nucleus during this beta decay. Now, as what happens is that as the mass number increases beyond some say 20, the number of neutrons in the nucleus they go on increasing and becomes greater than the atomic number. That means number of protons. Now these nucleuses have more number of neutrons than that of protons, and what happens is they become unstable and tend to go for beta decay. And what happens in beta decay is that a neutron in the nucleus is converted into a proton, and a beta particle is emitted, so that the ratio of neutron to proton decreases. It decreases in the distinguished nucleus that we obtain out of it. Now, if we take an example of it, phosphorus 3215, it gives S 32, 16, and a beta particle comes out of it. Now, what happens actually? You have a neutron, and this neutron converts into a proton and an electron-like particle. So this is our beta negative decay. Now, if we have to talk about the beta positive decay, now talking about beta positive decay, what happens in this case is, in this decay, what happens is a proton is converted into a neutron. So you have a proton, it's converted into a neutron and a positron is emitted. And why this thing happens? If a nucleus has more number of protons than that of neutrons, then the nucleus becomes unstable, and in order to have some stability, the nucleus emits, in the nucleus there is a transition. A proton converts to the neutron, and a positron is emitted out of the nucleus. And what is this decay called as? This is called as beta positive decay. And the example for this is neon 2211, and this neon 2210 is obtained, plus a positron is obtained. All right, so this is the case of what we call as beta positive decay. And this process can be shown here in terms of proton converting into a neutron and a positron. Now the third one is the electron capture. Now, in electron capture, what happens is that a nucleus absorbs one of the inner electrons. It absorbs one of the inner electrons, revolving around it, and hence a nuclear proton becomes a neutron. So if you have a proton, it will be neutralized by the charge of this electron, and this kind of beta decay is called as electron capture. And in this case, what happens is you simply have a proton and an electron which is captured from the orbit of this atom, and you get a neutron out of it. And this phenomenon is called as electron capture. And this electron capture is comparable with positron emission, as both the processes lead to the same nuclear transformation. What is that? In both the cases, the nuclear charge Z decreases. It decreases by 1. That's clearly understood. And however, the electron capture occurs more frequently than positron emission in heavy elements. This is because the orbit of the electron that we have in the heavy elements has small radii. So hence capturing an orbital electrons is very close to the nucleus. So electron capture occurs more frequently than that of a positron emission, what we called as beta positive decay. And this electron capture process is identified by, if the electron is captured by the K shell, if this electron capture is from K shell, we call it K shell capture. And if the electron capture is from the L shell, then we call it L shell capture. So these are the conventional bases for understanding the beta decay in these nucleuses. But now the point is that the energy that's carried by the beta particle, if we take the case of beta negative or beta positive, the energy that's carried by a beta particle, it has a spectrum. And we want to have discussion on beta decay, and we want to we will see that the reactions that we have talked about here, they have a flaw. They have a flaw because they cannot explain certain things. So we would like to discuss. We would like to discuss those things in the next video, where we will talk about the hypothesis, what's called as neutrino hypothesis, and to make these reactions complete, so that there is conservation from both sides in all the three nuclear reactions that we have talked about in beta decay.